The title is the Lessons Learned from Fukushima Daiichi Nuclear Accident. Presenter is the Mr. Hideki Masui. Masui-san is the Executive Officer and Deputy CNO, Chief Nuclear Officer of the Tokyo Electric Power Company Holdings. Please, Masui-san.
Okay. First of all, I'd like to thank you for inviting me here. And I think that it is our obligation as an engineer of the TEPCO to share what happened in the Fukushima accident. And actually, this is my second trip to the Estonia. My first trip is 10 years ago. I came here as a tourist. And I never expected I'm coming back here, my business trip. So I am very glad you are going to be considering the introduction of nuclear power very seriously. And I hope my talk or presentation will be useful, more or less. Okay. My presentation basically consists of 3 parts. The first part is an overview of the Fukushima accident. I'm going to give you a rough idea with what happened. And the second part is the lessons learned and the safety upgrade, which we are doing right now. And of course, this second part you can learn from a lot of lessons on your side. But the third part is dedicated for you because this is a lessons learned from your point of view for the country which is going to introduce the nuclear power right now. So in other words, the third part is, you can say, this is my personal, humble advice to you. First, I'd like to begin the overview of Fukushima accident. And this is a map of Japan. And we had, before the Fukushima Daiichi accident, we have 3 nuclear power stations right here. And in total, we have the 17 operating reactor. And as you can see, this blue area right here shows this is Tokyo. This is basically our service area. So now the market is deregulated, so it's up to us. You can business anywhere inside Japan. But still, we have very strong customer base around this area. If you take a look at the location of these 3 plants, it's outside our service area. So that situation makes us very difficult to have a good relationship with local people. And as you can see, we have the Fukushima Daiichi. This is the main topic of today's. And 8 kilometers away from the Fukushima Daiichi, there is the Fukushima Daini. And all those 10 plants has been right now in the middle of the decommissioning work. So that means we have lost 10 reactors. So what about this one? This can situated in the different side of Japan called Kashiwazaki-Kariwa. We are now trying to restart this plant. And I'll come back to the situation in the later part of my presentation. This is the outline of Fukushima Daiichi. If you take a look at it closely, we have 6 units, but the unit 1 through 4 are a little bit separated from 6 and 7, or 5 and 6. And this is some of the data for each unit. As you can see, Fukushima unit number 1 is our first nuclear power plant. It is commercial operation. It started in 1971, and it is main contractor of General Electric. And this is the earthquakes information which happened March 11, 2011. And it was a very huge earthquake. The magnitude is 9.0, and we have never experienced something like that. And the death toll is right here. It's 18,400, including missing person. But it's now a little bit. The number has been changed. It's around 1,900 or something. And this is this epicenter of the earthquake, and the distance between the Fukushima Daiichi is 177 kilometers. And this is another way of showing how big is the seismic energy. As you can see, our past seismic event, it has been the largest one. The size of the circle shows the magnitude, the level of the energy which has been released by the earthquake. So you can see this is a very big one. And if there is a magnitude difference in one, okay, magnitude 8 and magnitude 9, this is in terms of the energy released is different 24 times. Okay, so first I would like to talk about the earthquake impact caused by this earthquake. So there is some people say the Fukushima Daiichi caused by the earthquake, but it's not really true. Caused by the tsunami. I will prove one by one right now. And this one shows acceleration of the caused by that earthquake. And in each level, we have the two values in each cell. And the upper side is observed value, and the lower side is design value. And if you take a look at those three areas, observed value exceeds the design value, so it looks like a big deal. And however, this is our position. No significant damage to the safety-related SSC system, structure, and component were caused by the earthquake. We have three reasons for that. The first one is the plant response between earthquake and the tsunami shows no indication any significant event, like a loss of coolant accident or main streamline break. And the second one is a seismic response analysis shows no damage on safety-related SSCs. The third one is walk down of Fukushima Daiichi, Unit 5 and 6 shows no damage on safety-related SSC. Why it's Unit 5 and 6? Because Unit 1 through 4 has been severely damaged because of the high radiation. We cannot really go inside of it so easily. And I will show what we have found by that walk down. And this is an example of seismic response analysis. We have picked up some of the Unit 1, 2, 3, and safety-related systems, like here. On the left-hand side, we have the calculated value. Calculated value where we have the input of the actual seismic acceleration into the system, and we get the result. This is calculated value. On the right-hand side, you see the assessment criteria value. And as you can see, in most area, at least for this estimate, in the old area, assessment of criteria value is more than the calculated value. So this is a walk down of the Unit 5 and 6 reactor building. Of course, Unit 5 and 6 has a very severe acceleration. But when we take a look at the safety-related component, it looks intact. But this is not the end of the story. If you take a look at the non-safety area, especially in the turbine building, there was some damage you can recognize. For example, there is some laving mark for low-pressure turbine, and as you can see, there is a displacement of the piping system from the support. And yes, this one is also some displacement, and some small piping system has been damaged, but they are not really safety-related system. Okay, I'd like to move to the tsunami. Before going to the impact on the tsunami, I'd like to talk about the damage caused by tsunami on the general building and the local community. As you can see, this is a tsunami is quite high rising down there, and also, as you can see, we have the embankment surrounding our seashore area, but it has been easily overflowed. And the house has been washed away, and also there's a cruise ship was left on top of the building. Just by taking a look at this, how severe you can understand that tsunami impact is. And this is another picture is taken by some offshore camera. And this is this one shows the height of the splash. Splash means the tsunami came to the seashore and like this. So this red line shows the height of the top of the building, the unit 4 reactor building. This is 56.4 meters above sea level. As you can see, the splash is higher than that. Okay, this value right here shows the height of tsunami at the Fukushima Daiichi. On the lower cases, you see the 5.7 to 6.1 meter is a design value of tsunami. How we have calculated this one, because we dated back to the past history of the tsunami and made a calculation, and we submitted this value to our authority as a part of the licensing application and to get the approval to operate it. However, actually, the observed value of tsunami is much higher than that. Please be careful, and this is not 11.5 to 15.5 meter is not really the height of the tsunami, because we have tsunami height meter offshore, but it has been overscaled. We do not have the exact value of the height of the tsunami. This was inundation height. If you have the flooded in your site, you will see the mark in the outer wall of reactor building or turbine building anywhere. So that means this is the inundation height. So that means the flooded height, I would say. So this is how the tsunami caused damage. You can see the seawater pump has been completely damaged because it is located very close to the seashore area. And also, this is some sectional diagram. As you can see, all the site, even if in the backside of the reactor building has been completely flooded. So as I explained, it's 50.5 to 15.5 meters is this height. It's not really the actual height of the tsunami, but it's, again, the inundation height. And this is another way of seeing this. On the left-hand side, you see the Fukushima Daiichi, and it has been completely, entire site has been submerged by seawater. On the other hand, and on the right-hand side, you have the Fukushima Daiichi, which is located 8 kilometers away from the Fukushima Daiichi. The extent of the submersion or flooding is not so significant compared to Fukushima Daiichi. But the Fukushima Daiichi barely escaped the severe accident because external power as well as emergency power is available. So that's the difference between the Fukushima Daiichi and the Fukushima Daiichi. Okay, this is another picture showing how tsunami attacked our site, and you can see the seawall has been damaged and overflooded. And this is an interesting picture, and you see this is taken from the Loud Waste building in a high elevation area. This is a site elevation is 10 meters. And the tank, the height of this tank is 5.5 meters. So as you can see on the right-hand side, the picture, it has been completely submerged. So that means at least 15.5 meters inundation we have experienced. This is a very simplified event at the Fukushima Daiichi, and on March 11th, we had an earthquake. And the earthquake, at the same time, we have the loss of off-site power. That means we are not really use any off-site power, because off-site power is a general structure. If you have the huge earthquake, you cannot rely on that. But in case of the loss of off-site power event, we have an emergency diesel generator inside the reactor building. And this time the turbine building. And it has been started as designed. So that means right after the earthquake, it has been within the design basis event. I already didn't tell this one. The reactor has been successfully shut down by scrum mechanism. And then 40 minutes later, tsunami came to our site. So Tsunami has been completely submerged our site, so diesel generator has been lost. That means total power loss. So this is not a design basis event. This is a beyond design basis event. And then at that time, Unit 1, 2, 3 were in operation. Unit 4, it was being outage, no fuel inside the reactor. And I will explain later more detail. The first critical event has been the hydrogen explosion of Unit 1. This is just within the 24 hours since we had the tsunami. And this explosion made accident shooting is quite difficult because it was scattered of the debris. And also, we have the Unit 3 and 4, we had the explosion. And also the Unit 2, we have lost the water injection. And this is, again, the simplified event for the Fukushima Daiichi Unit 1. Again, the March 11th, 1446, we have the earthquake and the loss of off-site power. Then the reactor has been successfully scrambled and the emergency disease startup. This is, again, within the design basis event. And then the isolation condenser starts. Isolation condenser is a passive safety system, but the operator manually closes one of the valves because the reactor has been very, very quickly cooled down. And then tsunami came, the station blackout completely, and we have lost the power. Daiichi is lost, and the Daiichi power for the INC instrumentation and control has been lost. And we realized that we are losing the reactor inventory, I mean, the water inventory inside the reactor, so we're trying to do anything about that. So on the next day, the March 12, we started injection of the fresh water. I will explain in the next slide what we have done. Then we have realized that the PCB, primary containment vessel pressure, has been elevated. So we are trying to line up PCB venting so that protects the integrity of the containment system. But then after 4.5 hours, we recognize there is a depressurization primary containment system. That means success of the PCB venting. But right after that, just 1 hour after, and we have seen the hydrogen explosion at the reactor building. So this is a water injection. We had improvised this action. This means, okay, usually if something happens, you have the ECCS, you have the pump, and you have the water sources. But this time, it's not available because we do not have power. So what we relied on is a fire engine, this car. And this is for basically the event for the fire, but we have improvised this one. We have this one connected to the underground fire protection tank, and it has been connected with a fire engine, and then try to put the water in this line, existing line. But considering the amount of water we have lost from the inside of the RPV, the amount is not enough. The volume is not really enough to this operation. And this one is for the PCV venting, and we have realized inside the pressure, internal pressure of the primary containment vessel is elevating. And if it left unattended, it may rupture. It may rupture. I mean, it may lose the integrity of the containment. So that will lead to a catastrophe. So we try to create conduct the PCB venting operation. Why we are doing this? Because if we could successfully make this line available, we have the water in here, significant amount of the water in the suppression pool. So you can scrub the vented gas through this water. So some of the radioactivity, I mean, especially the particulate material, can be reduced through this water. So also at the same time, by depressurizing this operation, we can still protect the integrity of the primary containment vessel. However, we have the difficulty because usually these two valves are closed. And under the normal situation, we can operate it from main control, very quick action. But that time, it was not really available because the power is lost. So what we have done is we send a pair of operator in the field and try to open the valve manually. And first, there was two operators. Actually, they are the shift supervisor and relatively just senior people, because we cannot really let the young people go in the field because we have little knowledge about the radiation level in the field. So we have sent two people, and they came back and successfully opened valve. Oh, sorry, this one first. This motor-operated valve, they could successfully open 25%, like a manual operation. Then the second team was sent in the field to open these air-operated valves, but they could not make it because in the middle of their approach to that valve, they recognized there is a pretty much high radiation. So they decided, okay, we'd better go back. They came back. So the clock is ticking. So we have just changed the strategy. We have installed air cylinder outside of the reactor building and connected, and this one. So we could successfully open this valve from the outside of the reactor building. So then we realized there is a pressure has been decreased inside of the, inside of the primary containment vessel, and we recognize that this operation has been successful. However, hydrogen explosion occurred at that time. This is the schematics shows how hydrogen explosion has occurred. There's a numerous in the PCR, on the surface of the PCB, we have numerous penetration like electric cable, and also we have the equipment hatch. It has been usually sealed by special material. But the sealing capability has been compromised because of high temperature and the hydrogen has been generated inside the reactor RPV and also has been leaked out of the PCB, and the hydrogen is very light. So it has naturally is going up to the high elevation. So it has been accumulated on top of the reactor building operating floor, and finally it has been exploded.
Excuse me.
Yes.
Can you show by hand, because the laser is not visible on the screen?
Oh, really? Okay, I try. Okay, I try.
Thank you.
And okay, those are the penetration, and those are the key hatch. And if the hydrogen is leaked, go out like this, and it will come up like this. And the reactor building, the top floor is called the operational floor or a refueling floor, and you have accumulated the significant amount of the hydrogen, and it ended up with the hydrogen explosion. Okay, this is basically the same thing for the unit 1 and 3, but why the unit 4 has been exploded? Because I told you there was no fuel inside of the RPV. This was believed to be the backflow of the vented gas for the unit 3. Because for the unit 3, and this is a picture taken from the air, and this is basically the schematics like this. And we conducted for the unit 3 the similar operations, PCV venting. So if we conduct the PCV venting, the gas will go from this and then all the way to the stack and eventually into the environment, in the atmosphere. But however, this is an interconnected area right here. So some of the gas can be backflow from here to the unit 4. And the same story. We have the significant amount of the hydrogen in the top of the reactor building or unit 4, and it led to the explosion. Okay, this is a picture taken from the after the explosion. As you can see, the unit 1 has been exploded, and unit 3 and unit 4, we have the 3 explosions here. So I'd like to talk about how difficult it was to prime our initial accident shooting. And as you can see right here, the road, access road has been undulated, lots of cracks, so you cannot really easily approach it in the field. Also, there is a lot of debris can be scattered like this. There's another picture. You can see this one. This big tank is completely blocked access road. It has been swept away from the seashore area to the near the power plant because of the tsunami. So this one shows how difficult it was to understand the situation of the plant in terms of the operators. So right after this tsunami attack, the main control area became completely dark. There was no light. The only light we can rely on is a flashlight, which is equipped in the main control room. So they are having difficulty and work under the darkness and trying to read the, some of the parameter, like a water level and the pressure level, by using the flashlight. And we have connected some of the, because we have lost almost all the power, so that means we cannot really read the parameter of the in the main control room. So we have brought in some of the battery to the connect so that we can see the readings. And this one shows the operator with a full face mask in the main control room. Of course, operator is very, very good, very accustomed to the wearing the full face mask in the field, but not in the main control room. This one shows how frequent we had the aftershock in this after this earthquake. On the this one horizontal axis shows the days from main shock, and this is a vertical axis shows the number of aftershocks. So this tsunami is pretty much more frequent aftershock compared to the past earthquake right here. Okay, this one called the seismic isolation building, and this is basically the state-of facility, and almost all the command and control can be conducted from this building. And we have constructed this facility from the lessons learned in 2007 earthquake, which is attacked not Fukushima, but Kashiwazaki-Kariwa on the other side of Japan, 4 years before the Fukushima accident. And at that time, this control room, emergency response center, is located inside the general office building. It's not seismically so resistant. So what happened at that time is we had a difficulty go inside the emergency response center because the entry door, which is made of the steel, has been deformed. So people cannot really go inside. So what we have done is taken out the white board like this, and we started collecting information in the open air, I mean the outside. So from the lessons learned, we have constructed this seismic isolation building, the first in the Kashiwazaki-Kariwa, which has been directly attacked by the earthquake in 2007. Then we extended our effort to the Fukushima Daiichi. So if it had not for this building, the accident management at the time in the Fukushima would be pretty much more difficult. And this is the typical meals during the accident responses: the breakfast, lunch, dinner. This is basically the preserved food inside the emergency response center. It's not really tasty, probably, and not really sufficient in terms of the calorie as well as the nutritious balance. And this one always very, very popular. If we have the 3 instant noodles, everybody raise their hand, I want to take it, like this. But anyway, you can probably understand how difficult the accident response situation, at least initially. Okay, I'd like to talk the lessons learned and the safety upgrade we are conducting right now. So this is, I'm not going into the detail. What we have done is, fact, we have collected lots of facts observed in the course of the Fukushima accident, and I try to what is behind that. And very simply, and the cause of accident is insufficiency. There is 3 insufficiency. First one is a measure against the tsunami. And we have given so much consideration about on the earthquakes, but not on the tsunami, because everybody knows what is the most important natural hazard. What is that? What is that? I think that almost all the Japanese answered, it's the earthquake. So from the beginning of the nuclear power introduction, we have given the pretty much conservatism, or in other words, safety margin in every step of the, our design of our systems, but not for tsunami. And also, we could not really learn from international operating experience. There was a flooding event, at least we know that there was twice, in French power station, and we had the operational experience data at our hand, but we could not really make the best of that operational experience. The second one is insufficiency for severe accident, a lack of consideration of CCS, common cause failure due to natural hazard. And then last but not least, the preparation of the emergency response. We have conducted annual emergency response drill, but it is more of a ceremony than actual training. So we have analyzed those 3 issues and come up with 3 root causes. There is 3 issues, and the insufficiency, the first safety, first mentality, then technical competence, then third one is communication capability. And before I go into the detail about each items, I'd like to talk about the redefinition of the vision and mission. Right after the Fukushima accident, many engineers left TEPCO. They quit their job because they cannot really see the bright future in the TEPCO and the nuclear power. So we have to decide, we have to redefine our vision and mission. So to keep Fukushima nuclear accident firmly in mind, we should be safer today than we were yesterday, and safer tomorrow than today. We are committed to become the nuclear power plant operator that keep creating the unparalleled safety. This is our vision. And we have 2,700 people in our division, and you ask them, and any one of them, what is your vision? Probably some of them cannot really decide as it is, but they can say something like this. And I'll go to the what we are doing right now is in terms of the safety first mentality. And okay, this is some of the examples. For example, the first one is a reflection day of the Fukushima accident. Each year, March 11th, this is actually the date which occurred Fukushima Daiichi accident. This date has been dedicated to the reflection date. And what we do is we have a small group and talk to each other. And what was wrong with that, what we are doing right now is good. And because we are doing this, because it's almost 11 years ago, and 30% of our workforce has joined our company after Fukushima accident. And then safety upgrade, I will explain in my subsequent slide. And also we are asking the international expert like this to have some advice how we can enhance our safety. And also what we are doing right now is a safety proposal competition. So we encourage all people, why don't you submit any proposal which can promote safety? And of course, safety enhancement involves a significant investment sometimes, but this one is very easy one. As you can see, this is the bulb. We have put the luminous paint on there. Even if we have a complete darkness, we can access to this area and easily find out which bulb to open. This is, I think, a good idea. We try to continue this effort. And from now on, I would like to explain a little bit safety upgrade work conducted for the Kashiwazaki-Kariwa. Again, we have 7 units, and 1 through 4 are a little bit far away from the unit 5, 6, 7. Those 6, 7 units, we are trying to restart first. It's still middle of the restart activity. We have not restarted yet. For unit 6 and 7 is, in terms of the output, is larger than that of the unit 1 through 5. And also reactor types are a bit different. This is the advanced type of REWR. And what we have done is first we have learned severe lesson, and we first take a look at the natural hazard. What kind of natural hazard we are going to have to consider? We picked up from the various documents. We have picked up the 44 natural hazards, and we have screened out some of them. Because, for example, the Kashiwazaki area, we have a lot of snow, but the snow is very important consideration. However, snow avalanche, we do not have the high mountain around the Kashiwazaki-Kariwa area, so we could eliminate the possibility of the snow avalanche. And after that, 11 event has been picked up, so that we have to consider the effect of natural event on our site. And this one, the mechanism of tsunami, and this is very simplified diagram. Usually the tsunami is occurred, you have the seabed fault, and it has been activated, there will be a displacement. And if displacement causes a change in the seawater level, so then the tsunami can propagate all the directions. This is a simplified diagram for that. And there is 3 influential factors. Some of the influential factors right here, the scale of fault location, and the topography of seabed, and also the geography of the coastline. So based on the new findings, we formulated a design base of tsunami. And due to the time constraint, I'm not really go into the detail. What I'm trying to say is that we took the more conservative position. For example, those fault is not really interconnected each other. But we took a bit conservative position, and what if those separated fault activated simultaneously? So because basically the natural hazard is, how can I say, it's an act of God, force majeure. Of course, we will make a best effort by collecting the past data and try to reflect on what we are doing right now, but still, there is a chances of the actual natural hazard can go beyond our expectation or assumption. And this is a result of the tsunami, and for the design basis tsunami, and it used to be just 3.3 meter for the Kashiwazaki-Kariwa area. And based on our new findings, it has been elevated to 6 meter, and also the run-up height is 8.5 meter. For the site elevation, this is the original site elevation for the unit 6 and 7. It is above sea level to 12 meter. And we have added 3 meter, additional 3 meters in embankment. This is because we would like to be on the safe side against any natural event, especially in the tsunami. And on the left hand, on the top of that, this is a different tsunami wall. From the unit 1 through 4, the site elevation is a little bit lower, it's 5 meters. So we have the same idea. We're going to protect our site up to the 50 meters. So we built this Tsunami, which is made of the concrete, it's 10 meters high. But this is not the end of the story. And in case, if something happens, this has been flooded, we could protect our reactor building by using that tsunami wall and a tsunami plate. And if it has been, it might be a chance, but it has been flooded. And inside the reactor building, if you have the safety important component, we have installed a watertight door like this. And still, if flooded, we have draining system, and this is a pump-up system. The water can be pumped up from the room, the outside area. And this is another consideration for the against the natural event. For example, this is for the tornado. And if you have the recognize there may be a chance of a tornado, we are supposed to tie down some vehicles because so that we can prevent those vehicles become the flying object and the damage to the safety system of the plant. And also we have put some protection net in the safety alarm system. So this is another picture of what we have done. This is mainly focusing on the mobile equipment like this, the car, fire engine, and this number 2, as you can see, this is a large truck. This was called the heat exchange car, and inside of the heat exchanger and hose and the pump. And in case of the emergency, it will come down to from the higher ground from this area and near the turbine area, and they put the water tank, the pump inside the water, inside sea, so that we can recover the heat exchange system. And also, this is a power supply car. And the important thing is just having those vehicles is not really enough. The important thing is that our own people, TEPCO's people, can handle it. This is the most important. Okay, this is another way of the safety upgrade system of the Kashiwazaki-Kariwa. We have installed a hydrogen recombiner inside of the reactor building, especially the operational floor, on a refueling floor, because there is a place the hydrogen can comes up to. And I will explain later, this is a filtered venting system, has been also installed. And again, this just installing new system is not really enough. The important thing is that you have to do it your own. You have to handle what you have installed. So we are now conducting a training for the emergency response on a regular basis. Again, before Fukushima, training, emergency response training is more of a ceremony than the actual training. But it's not like that. It is now, it is business as usual. So all the newly equipped material like a gas turbine generator, fire engine, we make our own people operate in full-fledged. And also sometimes the simulator is conducted with a limited amount of light so that you can handle the situation in the darkness. Okay, I'd like to move to the second part of that. That's a technical competence. What do you mean by that? What we are now doing right now is a do it yourself. Because if before the Fukushima, okay, let's say we are going to install the new system to our existing site. What we have done is usually do is just to pick up the telephone, then make a telephone call to the vendor, like Hitachi, Toshiba. And we are thinking about this system. Why don't you bring us the schematics and some related document? Of course, it's an easier way, but the heavy reliance on the vendor, you don't probably understand how systems work at your plant. So right now, we are trying to enhance in-house design, and this has been installed, almost already installed, it's a filtered venting system. So the vented gas coming here and after scrubbing in this area, and it will be go into the environment. So we have expected for the radioactive particle decontamination factor is 1,000. This has been designed by TEPCO and manufactured by the new guys. New guys means they have never done work associated with nuclear power. We would like to enlarge our area of in-house design. Okay, the third item is a communication capability, and it's quite important for you have the very good relationship with the local people. And yesterday, Mr. Yamamoto explained local power, local government has some special power. That's right. And also, it's very important for us to the local people to understand what we are doing. For example, we are conducting a periodical briefing session, and we are making letting people to understand what we are doing right now. And after that, we will take any question from the floor, so that we can let the people understand what they're doing, what the kind of effort we are doing. Also, we have done third item right here, and visit all houses in NPP located municipality. Around the Kashiwazaki area, more than 60,000 people living, and we periodically once a year, we will visit each household. Do you have some comment, or do you have an opinion about our company or our power station? And if there is an opinion can be corrected, we would like to utilize them, how we conduct our business. Okay, I will go to the final part of my presentation. And this is a lesson learned for newly nuclear introducing country. And again, up to now, probably you can learn from a lot of lessons learned, hopefully. And still, I would like to tell something about that. Okay, probably you are going to adopt the upgraded design. I mean, more advanced in terms of the safety, and hopefully in the economy also. But still, you need three elements right here: a safety-first mentality, technical competence, and communication capability. And safety-first mentality is okay, and you have to keep in your mind, safety upgrade design does not really eliminate the possibility of the unexpected accident. Even if you have the advanced design, you cannot really eliminate the possibility. And you have to avoid the self-complacency or overconfidence. Self-complacency and overconfidence is, of course, the root cause of the Fukushima Daiichi accident. I thought that our plant is very safe. What we have done, looking back my personal history, what we have done is how to enhance our plant in terms of economy, not in terms of the safety, what we have done. So don't worry about it. Oh, our design is new and different from the old school reactor like Fukushima Daiichi. Oh, never do that, please. And to cultivate safety-first mentality, strong organization and leadership, which understand inherent risk associated with nuclear power, is pretty much important. And always get connected with the world and learn from others' experience. As I explained, we have the full knowledge of the flooding event which occurred in France. And as well as also we have the different, I'll pick up another example. There was a document called the B5B, which is compiled by the NRC. This is the main purpose. Basically, the main purpose of the B5B is how to cope with a terrorist attack. But inside the document, it's not so complicated. It provides mobile equipment and get water sources, and also how to recover the power. And we have in the United States, we have the local branch, Washington office of TEPCO, and we have many people visited the United States. Also, sometimes meet with NRC officials, but we could not really learn from the B5B documented. If we know that B5B document, it's not really significant investment. Just buying a mobile equipment is not really expensive. Building such a huge tsunami wall could be very, very expensive, but having some of the portable equipment is not significant investment. Okay, the technical competence. Okay, don't let nuclear power black box technology. At the initial stage of your nuclear power introduction, probably your knowledge and your experience is pretty much limited compared to that of the vendor. But try to catch up them and gradually gain the technical competence. That means you have to invest human resources. And again, you have no idea of the extent of the natural hazard. So under this extreme situation, the usual procedure does not really work. So what is our last hope? The last hope is knowledge and experience of the operator with deep understanding of the principle and the design. And also keep an eye open to what is going on in the field. So that means, in other words, you'd better spend more time in the field, not in the office, because everything is going to happen in the field. Okay, this is my last slide. This is communication capability. Again, nuclear industry is based upon the trust and the understanding of the local community. Why is that? Because once accident occurred, they are the primary victims. They have to evacuate, they have to leave their home, and sometimes they lose the connection with their hometown. So that means they are the primary victims. We have proven that. We know that. And so you have to take extra caution, extra care to have the very good relationship with the local people and let the people understand what we are doing right now. And mind the gap also is very important between the industry and the general public. From the industry's point of view, we have a bunch of the safety engineer. Okay, we are safe. I think our power plant is safe because our PRA result is something like this. But that's not really enough for to gain and trust and local people. And because local people would like to have a peace of mind. Having the peace of mind is different from assuming the plant is safe. And how we are going to do this? Because there is no actually the magic formula, but risk communication is one of the key, I guess. And we appointed almost 10 people as a professional risk communicator and give them a special training to become. The main function of the risk communicator is not persuade the people our plant is safe. This is not their mission and there is no function. And our expectation for the risk communicator is to listen to people and sympathize the worry, concern, or whatever they may have. And usually there is 4 steps for the risk communication. And the first is the disclosure of information. What is the nature of trouble? What is your plant status? And we're not going to hide anything. We'll be completely transparent. Then we will explain. Explanation is just not the one way. We have to be in the both way. We have to listen to the local peoples and also the communication. Then by repeating this cycle, we can finally, hopefully, building that trust. And thank you very much for your attention. And now I'm ready to answer your question to the best of my knowledge. Thank you.
Thank you so much, Masui-san. Any question? Yes, yes, please.
Yes. First off, my name is Kalev, still from Fermi. Of course, we honor the people who lost their life in the Tōhoku earthquake and the tsunami, and the good people of TEPCO that dealt with the consequences. I have had, from safety perspective, one question that has been nagging me since I read the 2 books about the Fukushima Daiichi. And it's also in the report page of 56 in the EIA report that as required by the operating procedures, isolation condenser system was stopped and restarted several times by the operators to prevent the reactor from cooling down too quickly and causing thermal stresses. So obviously the event that led to the pressure build-out and core melt was that there was excessive temperature. And there is a, as you understand, significant gap in wording cooling too quickly, and the primary problem being excessive heat. Can you please help me describe, understand, really even in hindsight, was the procedure still, does that procedure of shutting down the isolation condenser system, in the hindsight, does it seem correct? Or does it seem at the circumstances that there were, that heating was the problem? Does it in the hindsight seem to be incorrect procedure given the circumstances? Of course, in the normal circumstances, indeed, the reactor should not be cooled down too quickly, but given the circumstances of the severe accident or loss of coolant situation, was that incorrect procedure in the circumstances? It's a little bit technical question for others, but it interests us because we are interested also in the boiling water reactor, where isolation condenser system is one of the key safety functions. Thank you.
Okay, as you have explained, this is a rather technical question. This time I did not really include the schematics of the isolation condenser in my slide deck because I don't really think it's a main topic of my talk. But basically the isolation condenser is a passive safety system, and out of 17 nuclear reactors, we have just only one isolation condenser is installed in the Fukushima Daiichi Unit 1. It has been replaced by an active component called RCIC because the steam-driven pump's reliability has been improved. So we have decided, okay, let's forget about the isolation condenser and go for the RCIC. And anyway, your explanation is probably why the operator is close the valve under the extreme situation. Is that right? Is that your question?
Does it seem correct in the hindsight that it was closed to have?
I tell you, because as I explained, excuse me, could you? I'd like to go back to the timeline for the Unit 1. Oh, it's all the way. It's all the way. Okay, and right here, okay, isolation condenser system. Those who you may not familiar with that system, isolation condenser is like a very big shell, and it has located in the 4th floor of the reactor building, and steam comes inside of the isolation condenser, and it has been surrounded by a significant amount of water. And without doing nothing, we can cool the reactor for 8 hours. See? And this isolation condenser stopped. And isolation condenser is a pretty much high capability. It can cool the reactor at 8% of full capacity. And that means if once this system has been in service, a reactor can be very quickly cooled down. And this is one of the main good things about that. However, and at that time, operators thought it's cooling down too quickly, so he worried about. and they have sometimes opened the valve and stopped the valve to see to make sure there is too much drop in the reactor coolant temperature. And why is that? Because up here, okay, after the tsunami after the earthquake and up to the station blackout, this is basically within the design-based event. I don't really think, therefore, the operator at that time can predict there will be a total loss of power. I think that is a position for us. So in hindsight, okay, there may be there is if the operator has a very special ability, or they can probably come to the tsunami, and this may lead to the severe accident. So whatever the drop of the reactor water temperature, we will leave it there. If it is your hindsight, it may be correct. But at that time, again, when the isolation condenser started, it is within the design-based event. Did I understand you? Did I answer your question correctly?
More or less.
Okay. And also, there is a discussion, but this is not the end of the story. Because the isolation condenser, as I explained, this is only Fukushima Daiichi Unit 1 have. No other reactor we do not have. So, no, I'm just talking about the TEPCO's point. Okay, there is a point pointing out, and there is another reactor which is owned and operated by the JAPC, Japan Atomic Power Company. They have the Tsuruga unit number 1, and they have the isolation condenser. The difference between those systems, the system is also the same. But the JAPC's people conduct the surveillance. So they know how the system works. And on the other hand, the TEPCO's operator have never conducted any surveillance on that. Because once isolation condenser is activated, there's a huge amount of the steam comes outside of the reactor building. So if you have conducted that surveillance on the isolation condenser, you will probably know that your system is working. But that's not the case of our Fukushima Daiichi Unit 1. So what I'm saying is, of course, there is some lesson. But at that time, before the tsunami came here, the operators closing the valve and opening the valve and trying to make things work intermittently. I don't really think there is nothing to blame. That is my point. Probably you are not a little bit unsatisfied, but okay.
If it would have opened, there would not.
Yeah, that's right. Okay, it just happened to the tsunami attack when after the operator closed the valve, and if it opened, okay, the operation is the open and close, and they repeated this operation several times. If the tsunami came while the valve is open, maybe the story can be different. Thank you.
Are there any questions?
Yeah, I have a question. What are the reasons or why in project you have a diesel generator on the ground floor? If you have a quite big risks tsunami in your region, why your regulator accepted this project?
Very good question. Because I have the similar, the question right after the Fukushima Daiichi occurred. I first started my professional career at Fukushima Daiichi, and at that time I know nothing about nuclear power, and my colleague takes me to the making a walk down to, okay, here is we have the diesel generator. I did not have any doubt of that. But after the Fukushima accident, why we had the diesel generator in the underground structure? because this is related to the history of nuclear power in Japan, at least in TEPCO, and the first unit of the reactor of being completely imported from the General Electric. It is a turnkey contract. So what the General Electric done is just they have imported the same design from the United States in Japan. But in Japan, we have to give extra consideration to the seismic issue. So if the seismic issue is considered, you have to situate your plant is half underground, not completely overground. So what I heard is that's behind the scene also. And because also there may be a chance that some people realize, okay, if the tsunami came over our site, we may lose DG's power, the function of the DG. But at that time, our assumption is that tsunami can be protected by the site elevation, height of the site, nothing else. That's the reason. Also, there is another explanation about that is basically the diesel generator is a very heavy component. The heavy component we would like to put on the lower floor because of the concern against the seismic issue. Did I answer your question well? Yes. Thank you. Okay, please.
Thank you. Two questions. First one, how many people died due to radiation in Fukushima accident? And the second question is, if you would have had the hydrogen recombiners, would the story be different?
Okay, the first one is, as far as I know, no people have been killed by the radiation effect. Of course, there is a different, maybe the people say different things, but as far as we are concerned, there was no victim directly associated with the radiation. However, we lost two operators due to the tsunami, because at that time, for the Unit 2, the shift supervisor let the two operator go to the the walk around of the plant, and they happened to be the basement area, and then the water coming in, and 3 or 4 days after we could recover their body, but it has nothing to do with radiation. And your second question is. Okay, let's say if we have the hydrogen recombiner at the operational floor or refueling floor of a reactor building, we could probably escape the possibility of the hydrogen explosion. So the things has been different, but I can't really say how different it was. Well, the only thing which escaped the hydrogen explosion in Unit 2, because we have on the reactor building, we have what we call the blowout panel, and the pressure of the inside of the reactor building, not primary containment, primary building is elevated, it will left open automatically. But this time, this Unit 2, that blowout panel left open because of the acceleration. So we believe the reason we escaped, that Unit 2 escaped the hydrogen explosion, because this is just by accident, by chance. We never expected to do that. Any more?
More? No? I wanted to point out another aspect from the presentation. The lessons learned from the Fukushima Daiichi nuclear accident show the management issues. This is management issues. He pointed out the insufficiency of the three items: just the leadership issues. Okay, so how insufficient it is for the required capability. The senior management have to concretely specify the goal to be achievement. This is so that the clearly lessons learned is the management issues. Thank you.
Thank you very much.
Anyway, shall we move to the lunch break? So at the right now the 12:30. So we have to the lunch break up to the 1:30, 1 p.m. 3 minutes past 1 p.m. 1:30.